Welcome to our AI in Art webinar. I'm Julia Upton, Associate Professor of Mathematics and Data Analytics at Hudson University and IEEE Maine Section Chair and the Chair of IEEE Maine Joint Chapter of Computer Society and Communication Society. Thank you very much for joining us. I would like to thank our sponsors, UMaine, Office of Vice President for Research, and IEEE Maine Section, IEEE Region 1, IEEE USA. We will have two talks back to back. And afterwards, I will ask the speakers any questions that you have. The questions that you have, please type them into Q&A, not into chat, into Q&A. So now, without further ado, I'm gonna introduce our first speaker, Pindar van Arman, an American artist and roboticist who designed painting robots that explore the differences between human and computational creativity. Since his first system in 2005, he has built multiple artificially creative robots, earning multiple accolades, including a TEDx talk, making the shortlist at Barbican Dev Art competition, and first prize in the Robot Art 2018. Welcome, Pindar. The floor is yours.
Oh, thank you. Thank you. Like when you mentioned those dates, I can't believe it's almost been 20 years now that I've been making AI art, because AI art has, as everyone's noticing, it's taking off. And it's only, let's see here, let me go ahead and share my slides. Let's see what's going on here. There we go. Okay. AI art has taken off, as everyone is noticing, like in the last 3-4 years. And it's not that AI art hasn't been around for like 60 years. It's been around since AI art was started, right? It's like as soon as there's new way or new medium or something, AI artists get in on it. They want to experiment. But 3 or 4 years ago, the GANs, generative adversarial networks and deep learning, convolutional neural networks, sorry to go into those technical names so fast, but I'll just say deep learning, that the neural networks, the circuits designed, or the programs designed to replicate or model what's happening in our own minds, got big and powerful enough. So let me give you a little background on my art and where I came from and where it's going and why this is important, or why this is important to me, and what this has to do with AI and art. So, oh, by the way, my screen has a bunch of strange things on it, but I'm hoping it's a clear slide for you all. If it's not, go ahead, Julia, tell me, and I'll try and clear my screen up. But I started, like I said, like 2005, building my own robots. At first, they were just like really simple algorithms, connect the dot, paint by numbers, and yeah, I even built them with wood, whatever I could find around, household objects. But as time went on, I started adding algorithms to it, improving the AI, realizing that not only could these things be printers, which is something, they pick up a paintbrush, dip the brush into paint and paint. And that's basically, if all it's doing is connecting the dots and painting by numbers, it's basically, for me, it's a printer, because it's just executing commands. So every couple of months, and like at least once a year, I would add algorithms to it to try and make it better. Some of them were simple algorithms like k-means clustering, where I'd sort the colors. Others were algorithms that tried to fill in compositions. Others were algorithms that actually tried to create a style like the one on the left there. And other algorithms even would try and mix colors, like the painting here called Eric on the left, where it would try and mix CMYK. But the big thing I added, and this was the breakthrough that really opened up the art for me, and also got me the accolades, is I added a camera. And the camera would actually watch what the robot was doing, and it would do feedback loops. And what a feedback loop is, it sounds like it's a big computational, technical term, but the feedback loops I first heard about them from Paul Clay, artist painter Paul Clay. He talked about like when an artist creates, an artist makes a stroke, makes a mark, takes a step back and sees how the mark did on the canvas, and then makes another stroke. And he does this in a feedback loop. And then the artist might do this at every brush stroke, and then halfway through a painting, step back, how's the painting progressing to make more brush strokes. And so when I added these cameras, I started recording what the robot was doing and started programming algorithms to respond to what was emerging on the canvas, and artistic feedback loops, very similar to how a lot of artists paint. So the reception here it gets even more complex. I'm not going to go into details on here. We're going to go into details on one algorithm today, but this is just the general overview. I have massive stores of my own art, historic art, and databases. And I also have, like, historical brushstrokes of all the paintings I've ever made. And so if you read from left to right, you can see all these loops, all these feedback loops. And as the GANs, generative adversarial networks, the top left-hand corner there, where the machine's actually imagining faces, that's what we're going to go into in detail in a little bit, right after this. But you can see it, like, my machine's trying to imagine things, in this case, imagine faces, and then paint the faces. And of course, this isn't the greatest face ever, but this is AI, and this is like really early. This is like from 2017, 2018, but really early. This is really early in the deep learning, cycle. So back when it was made, this was actually pretty. This is what won Robot Art 2018, and this is how the robot works. It imagines, makes marks, takes a picture of the marks to see how it's matching what it's imagining, and depending on how that's going, it makes further marks, chasing what's in its mind is a portrait of a face, and that's when it's going after a portrait. So how, like I was saying, how are these received? That's Jerry Saltz right there, probably the most famous New York City art critic. He once said of this that it doesn't look like a computer made it, in a review he did of my work. I usually leave it just there because his full quote was, "It doesn't look like a computer made it, but that doesn't make it any good." And then he went on to trash the art. But I'm like Hollywood. I just take that first 5 sentences and put that all over my web pages, so that it came out as a great review, glowing review, like 5 stars, at least from the part I quoted. But he wasn't ready. This was a review back in 2018, and no one was really ready. And to be straight, I'll be honest with you, when I look at the paintings here, they are, like, if we're thinking of AI, this is AI's painting at the level of like a high school student, right? It's not painting at a sophistication of someone that's a trained artist, or like someone that's dedicated their life to art. It's high school level art. No insult to high school students. I mean, art is art. So let's go into detail of like what I'm talking about when I say imagining. And I try and keep this as non-technical as possible, although I know I have a technical crowd here. But this is an AI imagined portrait. This is actually my highest selling piece of work. It was recently collected for it was. I avoid talking money on these talks, but yeah, this is my highest selling piece of work. So it did pretty well recently at auction, and it was created with a generative adversarial network, and this is one of those neural networks I was talking about earlier. And a neural network, and I briefly went over this. Neural network is computer modeling, or like a way of trying to with software model what's going on in our head. And I have visualizations here on the right of an artificial neural network. That's pretty much what the code looks like. And on the left, that's actually live neuronal activity. That's like, I don't know how they did it, but I have credits down there to Michelle Koykendall and Gareth Guvansson. I think they're out of Georgia. They somehow recorded brain cells and neurons firing. And you can see they look alike. So, you can't help but wonder they work alike, and I don't know, but my art seems to, my gut tells me they do. So still for the non-technical, how this works is you show it a lot of pictures, and then train it, and you define everything. And then when you show it a new picture, like in this case, we're showing it the Golden Gate Bridge, it breaks it down into pieces and feeds it through the neural network and does a prediction. My prediction here, this is neural network I wrote, got 65% chance that's a bridge as opposed to a cat, or all those other things. And mine are 65%, but Google's and some other ones out of academia, they're at 99% plus. You showed a bridge. I mean, these neural networks are good now. You showed a bridge, it knows with almost certainty that's a bridge. This is just a neural network made by an artist. So what is a generative adversarial network? And a generative adversarial network is something that works similar to what I just showed you, but it's not one, but two neural networks. The first one, and I'll introduce you one at a time and describe you how they work. But the first neural network is a discriminator and a generative adversarial network pair. And this is like, you can think of it as like an art critic, like kind of grumpy, like he's an art critic because he failed at being an artist, just very angry at the world. And but if you show him something like faces, he's an expert. This art critic is an expert at faces. And he's seen tens of thousands of faces because he's an art critic that studies portraits. So if you show him that picture of the bridge, he knows immediately it's not the bridge. And if you show him a picture of, here's my son. If you show him a picture of my son, he's like, yep, that's a face, that's a portrait. That's a discriminator's primary job. Right now, on the other part, the other neural network we have is called the generator. Generator is this free spirit, it's just like happy person that likes to make art, wants to create, doesn't really care about what they're creating, but just wants to add to the world and the beauty in it. And if you give this artist or this generator a task, you'd be like, hey, make us a portrait. Generator's like, sure, I'll do that, and tries its best at a portrait. And that's the first try. Here's the problem with the generator. This generator, when it starts off in a neural network, a generative adversarial network, has no idea what a portrait looks like. Like really is like naive. It's a bunch of random numbers thrown into the neural network that makes the portrait. And so this is what the generator creates and says, hey, check out my portrait, and asks the discriminator, the art critic, what it looks like. Art critic takes one look at it. No, there's no portraits in there. But this artist is undeterred. It's like, okay. You know what I did wrong? And the discriminator tells it a little about what about this piece of art looks like a portrait and what doesn't. And then the generator takes that critique and adjusts a little and retries. So this is after talking and making 80 exchanges. It comes back to the generator makes 80 adjustments and makes 80 new pieces and shows a discriminator, all of which a discriminator rejects, but provides feedback. And the discriminator looks at it again and rejects it, but says, in this case, you might say, hey, listen, these are not portraits, but I can see a little bit of cheek on the bottom there. Like you got the bottom of the face and the eye sockets going, maybe work on that. Generator takes that advice, adjusts the number in its neural network, tries again. Discriminator says no, tries again. What number are we at? We're 240 iterations. And at this point, the discriminator is like, I don't see faces there, but look, the top one and the bottom one, I can see sort of the outlines of a face. Keep on working more like that. Generator adjusts its numbers, 330 tries later. And this one, you can see the discriminator is starting to get confused, saying, look, I see ghost images of faces, but still no faces. But look, that middle one's perfect. Make yourself more like that middle one. Generator tries again. And you can see this is what is it, 440 tries. This naive neural network is learning to paint faces. Discriminator, look at this one. He's like, that might be, this might be faces. I can't be sure. 1,100 tries, and the discriminator is still 4,000 tries later. Discriminator, it's all subjective, right? 4,000 tries later, the discriminator is like, wow, those look like faces. These are totally imagined faces. They were trained from 10,000 celebrity faces. So these faces don't exist. And whenever you hear about deep fakes, this is exactly how deep fakes work. Well, no, this isn't exactly how deep fakes work, but this is how you can make, you can invent faces. Like every so often you'll hear that there's a Twitter celebrity that's been invented. This is this exact process with more powerful computers. But here's how a discriminator, which is trained on faces, trains the generator to create and imagine AI faces. And here's an animation of all 4,000 frames, or maybe animation of the whole process. And you can see how it starts at static and ends at a face. I'll let you watch that one more time as we're coming to a close. And I'll also have some thoughts on what this means. Like, what does this mean? All right. Oh, right. So, well, that's how it comes to a face. What I'm interested in as an artist, and I do a lot of art with, is this very first step where something comes out of nothing. You can see it's like darkness, and the generator just finally sort of zeroes in, and like a face comes out as nothing. And the reason I'm interested in that is because I can't help but believe or wonder if this is where our imagination comes from, parts of it. Marvin Minsky talks about, out of MIT, wrote Society of Minds, talks about how our brains might not be a single mind, but thousands of different minds fighting and competing with each other. And it's likewise the same for me at least, I don't know how to like prove or disprove that, for creativity. We probably have 1,000 creative agents in our head all fighting for them. And I can't help but thinking that when we imagine something, part of that algorithm that's imagining is a generative adversarial network in our brain. Like almost like, you know, when you see these things moving through latent space, you'll see deep dreams, other generative adversarial networks, and they look dreamlike. It's almost as if our brains, when we're dreaming, you know, we're walking into a room where we're going to see something we've never seen before, and our brain has to like build it up from scratch. Like if we walk into the Paris and we want to see the Eiffel Tower, our brain has to think of all the references we've ever had to the Eiffel Tower and build an Eiffel Tower for us to see in our dreams. And I can't help but think that this might be a generative adversarial network or a structure very similar happening in our head. At least that's what I see when I see these animations. So anyway, that's why I called this piece of art First Sparks of Artificial Creativity. I made about 256, I made exactly 256 of these portraits of skulls, or faces that end up looking sort of like skulls. And I think it's an interesting exploration of where and how our imagination works. And I think that's one of the big things with AI art right now is that they're actually, that's what is exploring. What is creativity? What is art? Where does creativity come from? Where does inspiration for artists come from? And I guess that's about it. And I'm looking forward to hearing the next panelist and answering any questions you all may have.
Well, thank you very much, Pindar. It was a fascinating talk. A reminder, if you have questions, please type them into Q&A. And after our next speaker, we'll have enough time. We'll have time left to address those questions. Right. Our next speaker. So we continue the topic of robotics with our next speaker, Dr. Vikas Dhiman. His talk is on imitating human driving using inverse reinforcement learning. Dr. Dhiman received the Bachelor in Technology degree in Electrical Engineering from the Indian Institute of Technology, Roorkee, India, in 2008. The Master's degree in Computer Science and Engineering from University at Buffalo, New York, in 2014. And the PhD in Electrical Engineering from the University of Michigan, Ann Arbor, in 2019. He's currently an assistant professor with the Electrical and Computer Engineering Department in the University of Maine, Orono. He was a postdoctoral researcher with the University of California, San Diego from 2019 to 2021. Dr. Dhiman's research interests include robotic localization, mapping, reinforcement learning, and self-control of robots. Right. Welcome, Dr. Dhiman. The floor is yours.
Thank you, Julia, for the introduction. Can everyone see my screen? I'll go into the presentation mode. Okay. Yeah, so yeah, when I was invited to this talk about art, AI and arts, I was a little bit confused, but I was like, okay, I'll give a talk, but the only way my research is related to arts in AI is if you call driving an art. And I think that could be true if you're talking about like circus drivers and F1 racing. But well, I'll share my thoughts on AI and art, but my work is primarily on teaching robots how to navigate the world and how to understand the world around them. And as we all know, teaching robots to do anything is really hard. And this is supposed to be a video. Okay, let's see. Never mind. So teaching robots to do things is hard. They fail all the time. And one of the reasons why that happens is because it's very hard to describe robots how to do things. It's very unlike physics. In physics, we get very simple equations in terms of mathematics. We get like E equal to mc squared, F equal to gm1 m2 by r squared. These could have been very complicated equations, but it's so surprising that they are so simple. And R.W. Hamming wrote an total article about it, how mathematics has been so successful in describing physical laws. On the other hand, cognitive science people, computer vision people have been struggling to differentiate between cats and dogs, and still there is no like a succinct small mathematical equation that describes the differences between dogs and cats. And that's where learning comes in. And Pindar described very beautifully how neural networks are somewhat related to our brains, but they need like millions of images to train what is a dog and what is a cat. They need millions of parameters, millions of those neurons to encode that information, unlike 3 characters or 4 characters in a physics equation. And I work with reinforcement learning mostly, which has been very successful recently. We have been able to beat humans in variety of video games, the Atari video games, even like the games that were thought to be unbeatable by computers like Go. And now we have a single neural network that beats both humans in both chess and Go. So it is supposed to be generalizable. And then and there have been attempts to apply the reinforcement learning algorithms on farm of robots so that they can get a lot of training data. However, before I talk about what's wrong with it, just a brief primer over what reinforcement learning is. So in reinforcement learning, we divide the system or thing into 2 parts: environment and the agent. Agent is the robot and environment is everything else. And agent takes some actions on the environment, and then the environment changes, and then environment gives back the agent some observation, and based on what the environment is, the agent gets a reward or not. Like it can get a high reward if something good happens, it can get a low reward if something bad happens. So if a car runs into some sidewalk curb, then it gets a low reward, but if it is like driving consistently in the lane, then it gets a high reward. So the reinforcement learning algorithm tries to maximize the reward, that is long-term reward, not just like immediate reward, and chooses the actions that maximizes this reward. However, so the rewards are telling the robot what to do, not how to do it, and reinforcement learning is responsible for figuring out how to do it. But even telling the robots what to do is hard. So this also comes in the traditional paperclip maximizer problem, where you can imagine a robot that is being trained to maximize the paperclips, and if we are not careful in specifying the reward, the robot might convert the entire universe into paperclips. I'll show you an example of a very simple scenario. So this is a boat racing game, and the obvious objective is to complete the race in the shortest time. But the video game makers decided, well, we want to make game a little bit interesting, so we'll add these green blocks that the board has to cover to get some additional rewards, just to make a race a little bit more challenging. But when we train a reinforcement learning algorithm that tries to maximize the game reward, it quickly finds that the completing the race is no good. If I just loop around and collect these green blocks, I'll get more rewards. So even in a very simplistic setting, like a video game with specifying the right reward becomes really challenging. And when you are thinking about like real life driving situations, then what is the reward for safe driving, defensive driving versus aggressive driving, versus ambulance driving, where you have to match the safety with the aggressiveness and reach the place faster. And I can't even like start to think about how would you specify a reward for generating genuine new art, right? The Stanford, I quickly looked up like how Stanford Encyclopedia of Philosophy defines art, and they say the definition of art among philosophers is disputed, and even the concept of a definition of art is disputed. So how will we specify it to robots? So I can't stop by wonder. So one of the solutions that has come up in literature is inverse reinforcement learning or imitation learning. So we won't specify the rewards. We will just say that you should do as I do, not as I say, which means we show the robot or the algorithm an expert driving, a lot of data from expert driving the robot around, and then we collect trajectories from the expert and feed it into reinforcement learning algorithm. So the goal of inverse reinforcement learning is to find the simplest reward function that explains the expert behavior. And this concept is not new. It was introduced by Kalman as far back as 1964, but the interest due to deep reinforcement learning and other such algorithms has been renewed in this direction. And so we had this work that was recently published about differentiable semantic mapping and planning. I won't be able to go into the technical details, and most of the contribution is due to the technical details. Basically, what we do is we take a traditional mapping and navigation algorithm for robotics and then make it end-to-end differentiable. So differentiability is the property of neural networks that allow them to learn faster than like a non-differentiable learning algorithm. So one of our contributions was that we were able to compute gradients across the motion planning block, which was not done before. And there has been a lot of work in this area, and most of the problems that researchers these days are dealing with, that what is the definition of simplest reward function? How do we encode the Occam's razor principle into mathematics? And there are many approaches to do that. How to do that efficiently. You can use a maximum margin principle or maximum entropy principle, that randomness should be highest, and that would give you the simplest and the most broadest reward function. And then this is a mandatory slide to show that our method works well against the baselines, and also shows some demos of what kind of data we collected in the simulator. So on the left is car driving in a Carla simulator. On the right, we are showing the semantic segmentation output of this image, where color encoding shows the type of objects depicted in the image. So like green are trees and pink is sidewalk, this dark purple is the road, and we want to stay within the road. And so this is during the training stage, how the expert is driving. We were not able to take human data in this experiment, but we used like an expert that knows how to drive well. And this is the agent trajectory. So agent learns to stay within the lane just from watching the expert. And so we also have some kind of intermediate representations, like how are we learning the cost encoder, which is the opposite of reward encoder. And this heat map shows what reward functions that we learned around the trajectory of the car. Moving on to my another work that I want to talk about. So in this work, we learned not just from demonstrations, but from interventions. So if the car is driving and it is about to make a mistake, and an expert is watching it, so it corrects the car. So if the car is about to go out of the lane and expert human driver is behind the steering wheel, if it is about to make a mistake going out of the lane, the expert corrects it. And that's how most Tesla drivers or Tesla data collection is actually happening in the real world, which is questionable ethically. So if you collect that kind of data, there is some kind of like wavy behavior because of experts' reaction delay. Like humans don't react instantly. So after they react after a few milliseconds, and then by the time the car has already swerved a little bit. So if you learn from that data, you might end up learning a wavy behavior. So we account for that expert reaction delay, and we say that we shouldn't learn on the detailed trajectories, but where the expert is trying to take us to. Instead of learning on the trajectory, we want to go to some kind of sub goals. So some temporary goal where the expert is trying to take us to. And so we make those adjustments to the traditional learning from intervention algorithm. We also do some kind of backtracking, so from the sub goal, so that we can correct for this expert reaction delay. And after adjusting for those limitations of state-of-art learning from intervention algorithms, initially it starts by learning like a wavy behavior, and then over time, it corrects itself to learn a smooth driving behavior. And this one was also trained in simulation environment first, but we were also able to extend this training to a real world toy car with 4 categories of tasks: pedestrian avoidance and pedestrian following, whether the pedestrian is coming from the front or from the side. And we were able to do this because this requires much less data than learning from demonstration. Only a few hundreds of corrections are required to train this model. So with that, I want to wrap back to what I started the talk with. So if it is so hard to specify what to do and how to do things to the robot. So what are the open problems and what are the future directions look like? So in my opinion, these are the 3 big open problems. So we have to hardwire or hard code something about the world into the robots. Even human infants, when they are just born, they can already recognize human faces. There have been experiments about tongue protrusion, that if you take out your tongue in front of a recently born infant, they can replicate your behavior. So we have to make the choices between what do we want to learn from data and what to hardwire. We could hardwire what is a good reward function, what does a simplest reward function mean, what features in the environment to focus on, things like that. And since we want to learn from less data and want to generalize it to new scenarios, we want to introduce more structure to learning, like hierarchy, causality, compositionality. And a lot of learning these days is happening in a way very disconnected from how humans learn. humans walk around like real world with a fixed body that almost stays the same throughout their life. Instead, we are trying to learn in simulations and from already collected data. So the future of robotics lies in learning in the real world. With that, I would stop and I'm open to questions. Thank you for your time.
Well, thank you, Vikas, for this excellent presentation. We have already a few questions in Q&A. Keep them coming. Let's see, it looks like the first question is for Pindar. What is the relationship between the printer with a camera, the ability to assess its work, and the generative adversarial neural network?
Yeah, well, thanks for the question. And yeah, this is interesting. This is what, so I'll tell you a quick story. One time I built these robots originally because I had a growing family and I wanted to spend more time with my family and like to be an artist, it's a lot of work. Making a painting is, 20, 30, 40 hours. So I thought to myself, wouldn't it be cool if these robots could do the backgrounds, connect the dots, put out a cartoon of the work and not go in and finish it, like cut my 40 hours down to 5 hours. So I could get the kids to sleep and just spend an hour, just working on my paintings while talking to my wife. I don't know, it's just more time with the family. So I programmed the robots to be very simple machines in the beginning that connected dots and painted backgrounds. And then one day I was off at work and I came home at the end of the day and I saw that the robot painting was only half done from where I expected it to be. I was, what's going on? And I looked in the brush stroke, something had malfunctioned and the brush had broken, it had collided with something. But the robot was so dumb that it kept on, not dumb, it was just a machine. It was just painting and dipping this broken brush into paint, even though the brush wasn't there. And then I realized that's when I realized it was a printer. And it could only really be, reach its potential as if it could see what it was doing. And I thought to myself, it had to be smart enough to actually, if it's painting and it puts a brush stroke down and the brush stroke doesn't appear, it has to be like, what's going on? I gotta, something's wrong, and either stops or fixes itself. So that's when I added the camera. I wanted to see every brush stroke and then react to the brush stroke to be smarter than a printer. And so the relationship with the camera and the robot is that the camera gives it real life feedback, like what Vikas was talking about. It's the agent interacting with the environment, and the environment telling it how the agent, the painting robot as an agent, is affecting the environment. And an unaffected, really cool thing about this is, all this generative artists and AI is kind of a generative art. We create systems and then we add randomness into the systems so that our generative art has variety. So it's not always, not this deterministic, the same piece of art comes out every time as we created an algorithm or a system to make this art. And what's interesting about that is this is the ultimate form of randomness, because now that the robot is painting and then using its output as input, it's this really cool feedback loop. And you'll see in my artwork, if you go into it and look deeply, is I use intentionally runny paints so that there's lots of running of the paint, and then the robot sees a mistake and sees paint go into areas it shouldn't be and then tries to repair itself. So this robot's in this constant fight with itself. And if I go into more details, and I'll stop right here, but if I go into more details, there's 24 algorithms, AI algorithms, all the way from k-means clusterings to a simple like contrast measurement to deep learning, like I discussed in my talk, generative adversarial networks. And they're just fighting for control of that brushstroke, like a bunch of creative agents fighting for control of how the painting will turn up. Without the camera, that doesn't work because it doesn't know what it's doing. And I'll leave it at that.
All right, thank you, Pindar. Another question for you. AI is like a blind person. What kind and how much of input and information is taught before it can draw something like a portrait?
Yeah, that's the perfect question. Yeah, the example I've shown you, I used the celeb data set, a celeb 100 data set. I'm not the best on the technical side of things, but but if you look up celeb 100, you'll find this data set. I trained it on 10,000 faces of celebrities, low resolution images of celebrities. I think it was 128 by 128 pixel images, but maybe it was 64 by 64, I forget. But right now, that celeb data set, which is a very common one used across academia and testing, I think it's over 100,000 faces of celebrities now. And as you saw, you train again on 100,000. Well, and the one I showed you trained on 10,000, and after 4,000 iterations, it gets pretty good at mimicking what was put into it. The one thing that's important is that data has to look alike. Like you'll notice in all of those, the faces are in the same place. Whoever prepared this data set with the Celeb 100 data set, they lined up all the eyes and they lined up all the mouths. So even though they're different celebrities, the eyes are typically the same place and the mouth isn't typically the same place. And if you train again on that, it'll come out with what you expect.
All right, another question for you, Pindar. How does AI and art relate to the development field of neuroaesthetics?
Oh, I don't know anything about that. I'm not sure about the field of neuroaesthetics. So like if you type in another, I'm going to look it up maybe and have an answer later, but is that, my guess is neuroaesthetics is what our brain thinks of as beautiful. I don't know. I'm trying to figure that out because I don't even know what my brain, I don't know what my brain thinks of as beautiful. And also what's interesting is to be a successful artist, here's the tip for, here's a tip for the artists out there. To be a successful artist is not as much as how beautiful your art looks, so that is important. It has to be very, very, interesting. It just has to be interesting. It doesn't have to be beautiful. It's more a deal of like, does all your work have a consistent message? And if someone sees a new piece of yours, so they immediately recognize that as a Pindar. For example, if you've seen a lot of Picassos, but you haven't seen them all, and you can be shown a new one, and you'd be like, huh, is that a Picasso? So Picasso has built this like, recognition system that has trained our brains to recognize Picassos. And that's more important to the success of an artist than how good it looks. Long-winded answer to the different question, because I don't know the answer to that one.
Yeah, there's a certain flux as far as humans are concerned. There's not only differences in how we perceive what's beautiful, it also changes, right? What we thought was beautiful yesterday is not necessarily what we think is beautiful today or will be in the future. So it's a very complex issue.
Yeah. Okay, I just add something. It's interesting. It's interesting that we agree more on visual aesthetics than we do on musical aesthetics. And that's what I think is really fascinating is visual aesthetics, we can all agree on that a painting is good, or like most of us. But music aesthetics, you can have gorgeous music, but it's just in a genre you're not into. And so there can be vast. So that's like makes it always complicated to me. What is good music? I don't know. It can be an amazing rap song that I love, but then someone else is like, I can't stand rap.
All right, next question ties in what we're talking about here. Do you think AI could be used to predict what paintings people will like?
I might leave this to Vikas. I'm not an expert on this, but are you, Vikas?
No, but I have opinions on everything.
Go for it.
Yeah, so as Julia mentioned that our preferences change and AI is used to trade and share markets, but we people are weird people, right? So if someone told us that AI predicted that this is going to be the trend next year, I'm sure people will make sure that that's not the trend next year, right? We want to be we have a tendency to be a rebellious tendency. We don't want to agree with people all the time. So it could AI might beat us to that. But if we told people that AI predicted, then I'm sure that AI won't be able to beat us to that. But it's an interesting experiment to try.
Yeah.
All right. So far, those are all the questions I see in Q&A. Let's see. Oh, there's one more. Oh, okay. Question for both speakers. For art, it seems the disorder added in the competing networks is important. Would an ill-conditioned training data set enhance the end result?
Yeah.
Like a genetic mutation resulting in a beneficial adaptation? Interesting question.
It's a good one. I have an answer I shouldn't talk about yet, but I hate to. Okay, I'll talk. I'll say, hey, look, this is the first time I'm talking about it in a public forum. I am fascinated with quantum computers because quantum computers have noise. And I'm fascinated in the fact that, like, if you make these generative art systems like AI art systems, I mean, theoretically, it's deterministic. If you start with the same seed phrase, it could be deterministic in that you'll get the same results over and over again because we just simulate random numbers. So I like to add dirtiness to my neural networks, and the dirtiness sort of bring out the humanity of it, make it less mechanical, make it look more mature, give it more texture. But I don't want to add the same way that I run these neural networks, and the same way I run feedback loops, in that I'm not gonna add random blemishes to my paintings. I'm gonna let blemishes happen naturally, and then I'm gonna fix them. I'm not gonna program the robot to make mistakes and then fix the mistakes, because that seems like a gimmick. I'm gonna make it harder for it to paint by giving it really runny paint and expect it to fix itself. And the results when that happens is great. In the same way, I'm finding out when I start introducing quantum noise, a superposition, I'm getting some really rich results. One of which there, you can see it over my shoulder. It's going to be at Sotheby's in about a month. I just think it just makes it much more mature. It's like, I'll put it this way. I could easily have perfect paintings, and everyone in this conference can too. If you get a photo of yourself and send it to your painting robot in your office, which is a printer, is a painting robot, and you have perfection. But I'm not after that. I'm after, like, some expression, some interesting, some layers and depth, and I add disorder into it, into the data, and I'm just always searching for natural ways of doing it instead of gimmicks or just random number generation. And it does enhance the end result.
Vikas, would you like to add anything to this?
Yeah, I think Pindar summed it very well. Randomness is important. In fact, what the generative networks that Pindar talk about already have randomness. There is conditioned randomness as well in some of the conditional GANs, where you can actually seed a generative network using some numbers, and if you seed it repeatedly with the same number, it will generate the same face. And if you move the number slightly different from the initial number, it will only make a slight variation.
Oh.
So those conditional GANs are very interesting as well. Like, people have made demos where they slide from one kind of face, say like a Barack Obama's face, to I don't know, Tom Hanks' face, and then it smoothly changes and generates faces that are seem like intermediate faces.
Wow.
From one to another. So yeah, there is some kind of randomness already in current neural networks. But what is interesting is controlled randomness. Art is not just random. How to keep it something interesting rather than just noise on the screen, right?
Yeah, do you mind if I add to that, Vikas? It's like one of the people often ask me, why do I concentrate on portraits?
Yeah.
And I do concentrate on portraits. And the reason I concentrate on portraits is, if anyone in here wanted to make a painting robot, you could do it by tonight. Go to IKEA, grab a Roomba, put a paintbrush on the back of that Roomba, or something that makes a mark, and have that Roomba bounce around on a canvas, right?
Yeah.
And that's randomness, but it's not controlled randomness. So I try and make faces because there's something about how our brain works, which I don't fully understand, where we recognize faces. And I'm trying to make portraits that are as abstract as possible, but still trigger that likeness reflex. If I was to do your portrait, Vikas, I would try and make it as random as Picasso, crazy as possible. There's some weird portraits, there's a portrait above. Let me see if I can point it. That's this fellow artist named Robin. Try and make it as weird as possible, but still trigger that likeness. And then you're okay, I'm working within some parameters. So there's some there's something going on here instead of just complete chaos.
Definitely. Yeah, I agree.
Go ahead.
And that's fun, and it just helps with the creativity and makes, because I think just random numbers and like putting a Roomba, that's not creative. There's like a creativity might be, I'm rambling a lot, but I don't know creativity. And I like what you said, Vikas, about, and I'd like to learn more about what you said about people can't even agree on the definition of art. But, you know, creativity to me is solving problems in a here's how I would define a quick definition of creativity. It's how we solve problems without using brute force methods, right? So, you know, there's a brute force method to do anything. But if you find a way that doesn't use brute force, you're being creative. And so that applies to a lot of things. Whether it's you're trying to figure out your kid's password and you could brute force it, or you can be like, oh, his girlfriend's name is Claudia, I'm gonna try Claudia something, right? That's creative solution to like, you know, snooping on his texts. I've never done that before, but this is used as an example.
Human creativity is as much of a black box as any black box as part of a machine learning system.
Yeah. So I'm curious, what do people here think about the definition of art? Because I have some, and I'm always curious what other people think, because AI is definitely challenging that. AI, I'll put it this way. I am very confident that AI is creative like us. Yeah. I think it is creative. Yes. I think we've reached that. It's obviously not an artist yet. So like, I'm curious what people think about AI and art. Like, I don't think.
Quick question for you, Pindar. What if your AI were to produce a Pollock-like painting? What would be your reaction?
Out of the University of Wisconsin, and I'm sorry I don't have his name in tip of my, but there was a Pollock bot in around 2007, and it made paintings that look like Pollock's, and would even measure the canvas to make sure that too much white, Pollock's had more blacks. It made black and white Pollock box. I actually bumped into the professor behind it. I'm gonna have to look it up while we talk. I bumped into the professor behind it at a conference, and we didn't know that we knew each other because we had chatted about his robot. There it is. Hold on. I won't get distracted, but you guys can look at. But okay, so it made very, very good Pollock robots. But was it creative? Yes, it was creative. Was it creative on the level of Jackson and Pollock? No, because Pollock came up with that algorithm. So, you know, the robot was missing the layer of sophistication to create the algorithm, but it could execute the algorithm. And so that tells you something interesting about human artists and successful human artists is after Jackson Pollock created this algorithm, he made hundreds of these, right? All these repetitions of these Jackson Pollock paintings were not any more creative than what a robot could do. He was basically executing his own algorithm. And then you realize that about the artistic creative process, and a lot of successful artists find an algorithm that's really good, people resonate with, and they repeat. And I find myself in that. If I have a successful, you know, it's reinforcement learning, Vikas. I get collectors collect a certain style of mine. I'm like, oh, that's the reinforcement I get. I'm like, I'm going to keep on doing this style. It's very popular. As far as being an artist, though, here's where it's not art. Here's why Jackson Pollock's paintings are art and Pollock bot's paintings are not. And there's only one reason. In my mind, my definition, Jackson Pollock told us it was art. That's it. Pollock bot has never told us these paintings were art. And that's the only thing that I need to think of something as art, that someone tells me it's art. Like another person that made it, preferably, sure. That another person says this is art. And until robots are persons, they're not making art. And that could be anything from a Pollock painting to if a robot arm took a cupcake and crushed it against the wall and then pointed at me and said, check out my art. I'd be like, okay, that's art. You know, and but the robot, of course, would have to be a person. And so that's what we're missing. And that's what, until AI has general AI and has something to communicate to us, it's not going to be making art. And I get a little, this is where I'm never negative on other artists, but I get a little irritated when there's a specific 3 or 4 AI artists say that their AI is making art and that their AI is an AI artist, the world's first AI artist. It's not, because I don't know. I'm curious what your all's opinions on that are.
All right, we have one more question that just showed up. How long does it take to make a painting? I'm guessing with AI, right? AI powered painting, yes.
1 to 3 days. If you go to my YouTube channel, I just live stream it all the time, so you can see them. There's hundreds of them, like just as they go through. So it takes 1 to 3 days.
All right. Any closing thoughts? We have still a few minutes.
Anyone like that's like, feel free to like comment in the questions about what you think art is, and if AI can make art.
There is still no consensus. It might be easier to define art by defining what's not art, but I'm not sure that's easier.
Well, I mean, it's easy. What if you told me someone was art? I'd be like, well, here, surprise! I present to you whatever you just said as my latest art piece, and then it's art. Like, so. Oh, someone put something in the chat.
If we another question here in the chat, if we wanted to get started on our own making AI art, not just art following an algorithm, other first steps you'd recommend?
Yeah, there are. Okay, so AI artists range from very technical artists like me to artists like Gene Kogan, who like way above me. He invents like GANs and interesting neural networks. I use other people's GANs and neural networks, incorporate them into my 24 algorithms. I've written my own, but they're never at the level of what I've gotten from other people, open source. I'm a novice at it. But you don't have to have any technical ability if you want to get started. There's a couple websites. Playform.io is one. There's another one called Artbreeder. And there's another one called Runway ML. And these, they get you started. They have little things, and you can just upload pictures of yourself. You can do type. You can upload like training data, like I was saying, the 10,000 faces. You can say, hey, here's 100 pictures of my dog, and then you can upload those and try and make a algorithm. And it's all plug and play, no coding. They typically use a free version, but if you want to do more complicated stuff, you pay a little, but it's never much. So I would find these websites. Off the top of my head, Runway ML, Artbreeder, Playform, Deep Dream. Look up Deep Dream, and you can make your pictures look like dreams. Yeah, that's a good way to get started. And then if you want to go more complex, you're impressed by that, and be like, I want to control the algorithms. Look up Google Colab Notebooks. And then once you're done with the Colab Notebooks, and you just bring the code onto your own neural networks on your own computer. This is great advice, actually, but I hate to admit doing this. I go search for people's homework assignments on GitLab and GitHub, and I steal them, and I grab them. And just they're as long as they're open source. If they're a good homework assignment, and the homework assignments always get the ones that are really good algorithms always get like lots of good reviews, and they're worth using. So
I also want to mention in the NeurIPS conference, that's the biggest machine learning conference, there is a track for AI for creativity and design, machine learning for creativity and design. So check out some of those talks. I guess those might have some good ideas and good networks. And about the question about whether art can be artist, one of our computer science professors, John Ippolito, actually sent us his article that had a very good review of like the legal cases where someone made a machine and the machine made the art, whether the artist owned the copyright or no one owned the copyright. So that was an interesting read. So it was sent by John Ippolito, from professor of me. He's a professor in the new media department. I guess we are almost out of time.
Yeah, unfortunately, we're out of time. I would like to thank again our speakers. Thank you, Pindar. Thank you, Vikas, and the excellent discussion that followed up. As far as coming attractions, the next webinar in this series will be at the same time slot on April 7th and focused on explainable AI. we're going to dig inside of those black boxes. Well, thank you very much, everybody who attended. And have a good day.
Thank you, Julia. Thank you, Pindar. Thank
Hey,
you,
thanks.
everyone,
Nice
for
meeting you
attending.
guys. And thanks everyone for being here.